So we're going to pay attention to this guy right there. Let's answer the following questions here. I'm going to pull this guy up a little bit, and I'm going to pull this guy up. We're going to figure all this stuff out. So the first thing is we have an RS. RS, anytime you have a Zener diode, you need to have some sort of source resistor in there. And that source resistor is basically protecting the Zener diode. That's what RS stands for. Call it a Zener diode protection. And you have to calculate that value. And in your textbook, it actually talks to you about how to calculate that value. And I'm just gonna get my notes here and to make sure I'm on the right track with this. So first of all, and we'll hook it up to a main bridge in a second here. The first thing we want to do is we want to calculate, and I did not put that down here, and it's one of the little problems we have on this. So I'm going to go ahead and annotate this, draw it out. First thing we're going to do is find what we call the max current, and we call that IS. First of all, we need to know what the power total is. This part right here is what you want to have on your circuits. For this case, IS is going to be your watts, your max watts. Call this max watts. Divided into your voltage. And I'll tell you what the voltage is in a second here. So this voltage is our Zener voltage. So that's why I'm going to annotate it with a Z. It's not going to be our source voltage. It's going to be our Zener voltage. So in this case, we take and we want to find the IS on here. And we take and do some math. We're going to take math. So go ahead and then just put this stuff on. You're going to tell me what you get on here. So we got the max power, then watts is 1 watt. And then we divisible by your Zener. This size is 5 volts. So what do you get on that? Somebody tell me what you get. And write that down. Or type it out. Okay, 0.2.
0.2.
Yep, 0.2 or 200. I'm going to put down, actually, I'm going to put down 200 mils. Yep, good, excellent. So I'm going to go ahead and I'm just going to put down, I'm going to put it down as 200 mils. Good. So that's our current through the IS, which is up toward the top here. That's the current right here. So that's IS. So next thing we want to do is find RS. So RS is, if you don't get RS, you need to find RS. And a lot of times it's just, it's easy to calculate it. So RS, that's not an S. There we go. RS is going to be equal to your V source, that's S, V source, minus V Zener. And that's going to be over your I. Yeah, I'm just making sure IS, yes, it's IS. So go ahead and let's put the values into this one. So your source voltage is 12 volts minus 5 volts divided into 200 mils. Jeff, can you tell me what you get on that, please?
That's 35.
35. Okay, so it's 35 ohms. Okay. Any questions right now in regards to any of the math we're doing on this?
Yeah. How did you get the 5 volts Zener?
Okay, so the Zener is what I picked out. Let's say that I'm the engineer and I'm going to you and I'm saying, okay, let's make sure that my brain is working correct today. I designed a circuit. Can you do the math for me on this? So I gave you a 5 volt Zener. Will this work? You know, maybe we had a circuit that blew up and we had to build one, and you guys came to me and said, as a maintenance person, he came to me and said, hey, I need something that's going to make this thing work. And I said, okay, here's a circuit. Here's your 5 volts that you need. So that's how I came to you. And so this Zener right here, unfortunately in the Zener, they usually do not put the values. You have to know what kind of Zener it is. That's how it is. You know, engineer will come up with that, okay?
So this is a rating of the Zener diode, not the actual voltage that's flowing through it.
No, the voltage that's flowing through is how much? How much would be flowing through?
12 volts.
12 volts, right.
So what is where did the 5 volts, is it termed
That's
a
5 volt
rating?
Zener. Yeah, it's the 5 volt rating of the Zener diodes. That's the rating of it. So Zener diodes have a rating of voltage, and they're regulators. That's what a Zener diode is. It's a cheap regulator. You want cheap? That's it right there. They're great. They're great when you want to, you know, if you're not having a high current application and you're just trying to get something to work. Perfect opportunity. Perfect.
This is a specification, a given.
Yes.
Of the Zener, not something we would be calculating.
No, you would not calculate. You could go to Mauser Electronics and pick up a Zener. You go there and just Google it, and you say Zener, and also you're going to come up with 10,000 different values you get out for a Zener. And then you're going to be like, well, great, you know, which one do I want to use? So the biggest thing is anytime you have to replace a Zener, number one is you want to make sure you get the correct voltage. Always the correct voltage. It doesn't matter on the current. It's always the voltage. Because if you put in a Zener that's meant for, let's say you're fixing a board and you had a Zener and you looked at the schematic, it said it was a 6-volt Zener down there. But they give you a part number. All you have to do is go into Mauser Electronics or one of those electronics and say, oh, I need 6-volt one. And you get it. But let's say you decide you're going to get a 12-volt one. You just blew up your circuit right beside you. You could blow things up down the line. So always pay attention to that. Current, get one that's heavier for current. The problem is you get one that's bigger to handle more current, it's going to cost you more money. It's going to cost you more money. So just keep that in mind. Also, Zener diodes, and this is for like Victory, you know that you're into being a tech. If you ever get to board repair, keep the Zener diode off the board. Always keep it off the board. You want to make sure that it gets a little toasty warm. You're not cooking the board. And that goes for anybody that goes as being a tech, okay? That's some FYI too on that, all right?
So Charles, does the voltage on the Zener have to always be lower than the source voltage?
No, your source voltage has to be higher than your Zener. So this case, if I had...
Right.
Yeah. All right, so if it was equal, believe it or not, if it was equal, your Zener diode is, let's say our source voltage is 5 volts and our Zener is 5 volts. In all honesty, you won't get 5 volts out of that Zener because you're going to have a little bit of what they call wiggle room in that Zener. And you may only get 4.5 volts out of it. That could affect your circuit. So always keep that in mind. Always make sure that your source voltage is larger than your Zener, but always don't change your Zener out and just say, I want to give myself a 10-volt Zener, because you could destroy things down the pipe down there. I've seen that happen where people have changed out the Zeners and they forgot to look at the spec on it. And they thought, well, I have one on the shelf, and they didn't look at it, and it was like a 15-volt Zener. And yeah, all you need was a 3.6. You just cooked out a couple of comparators. So just keep that in mind. Okay, makes sense so far? Good. Okay, so 35 ohms. So I have to change this RS out to 35 ohms. That's not a big deal. So that's 35. And believe it or not, this is just a Zener protection. This is Zener protection. It's just keeping your Zener. You don't ever want, okay, think about this. If you ever take and you dump a huge amount of voltage into any type of regulator, it's going to be screaming at you. It's going to go from 0 to ramp way high. You don't want to do that. You want to give it a nice, steady increase. So that's what RS does. So RS is going to be in series with the Zener. It'll always be in series with the Zener. Okay, voltage across a load. If this is a 5-volt Zener like it is, this is a 5-volt Zener, what should we get RL should be? Drake, what do you think RL should be?
Say that question one more time.
If this is a 5-volt Zener, what is VRL supposed to be? What's your voltage across the load?
It'd be still 12, right?
Nope, because remember, the Zener is acting as a regulator. So what if this is 5 volts? What would this be then?
So that would be 7?
No, it's if this is 5 volts, this is going to be 5 volts.
Okay.
So just remember this. Think of this Zener diode as a battery. Okay, think of Zener diode as a battery. Okay, always think of it as a battery. Okay.
Okay.
So if this is 5 volts, if this is 5 volts, this is going to be 5. If this is 3.2, this is going to be 3.2. It doesn't ever matter what this guy is. All this guy is saying is, I can give you 12 volts up to 12 volts if you want it. That's all it's saying. Hey, I got 12 volts to give you. But the Zener's like, I only need 5. You keep the other 7 for now. Okay. Okay, let's see. I'm going to check to make sure we're on track. By the way, there is questions that I threw our last math on here. So let's see, what else do I want to kick on here? RS, RL. Okay, let's do IL. Let's do IL. I'm going to bring this down a little bit. I'm going to clean off this board. I got to bring things up, and I know it's going to move around, but that's okay. And I'm going to turn the simulator, and then we're going to do another one with a Zener, with some of the Zeners I have over here. So we'll see if it actually works. Well, actually, and I've set it up, and you're going to help me with that. So we'll do a. Yeah, I hit the wrong thing. So the RS was 35 ohms and 5 volts, and IRL. There we go. So my IRL is going to be, well, we're going to do, that's the load. So we're going to take voltage of the Zener, and that's going to be divisible into the RL. So this is 5 volts, which is right here. And what we're going to do is, and we're going to drop this. I'm going to drop this to 100 ohms because I don't have a 1K on me. I'm just going to use 100 ohms right now over here. I'm going to see what I have over here, but for now, I'm just going to use 100 ohms. So 5. So somebody tell me what it is, what you get on that for with the 100 ohm resistor. Anybody?
0.05.
Okay, so 50 mils. Excellent. All right, so we got the IL. And let's see, what else I want to do. Let's do one more. I'm curious to see what I Zener is. So basically what I Zener is doing is seeing what the current is going through that Zener. Let's see what happens with that. So first of all, I needed the IS. And that was, how many mils was that again? Jeff, can you tell me how many mils that was?
0.2.
0.2, so 200 mils. Okay, 200 mils. Okay, so we have 200 mils. Well, this is just using, since these are parallel circuits, all I'm going to do is subtract this current from this current, and I should be able to get it. So IS minus I see, hold on a percent. Sorry, this current minus IS, which is a total, should give me that guy. So I'm taking a source one, and I'm subtracting off, and I should be able to get that. So if I take 200.
Charles, just interrupting for a quick second.
Yes.
Is that IR or is that IRL?
Sorry, this one down here. That's IL. That's IL. Sorry about that. So if I take IS minus IL, I get I see. Which makes sense because we have, this is just a parallel circuit, so I'm taking my total current and subtracting it off. So that gives us 200. So this gives us 150 mils. So far, so good?
So um, well, I'm not even trying to ask the question, Charles, but
Sure.
If you can scroll down a little bit back to the circuit.
Okay, hold on, let me go back to it, sure.
Okay, so the Zener diode here is acting, you said, like a battery.
Yes.
And it's because it's rated at 5 volts and it's getting more than 5 volts, it's limiting 5 volts to the load.
That's correct.
Okay, so the rest of the voltage has to be consumed up in the resistor, which is why you need the resistor.
Yes, it should be, well, it's a small resistor right there, but the rest of it should be dumped into there. Yeah, the rest of it, we can actually solve for that one too if we wanted to. This is a combination circuit, so it's, it's just a matter of looking at it and see what we have on it. So if you have 5 volts to it, the rest should be about 7 volts across that, approximately.
Okay, so so hang on one sec.
About 6 volts on it. I'm calculating about 6 volts on it.
Well, again, that's a 35, not a 30, you said.
Yeah, this is 35.
Yeah.
I'm just giving an estimation about.
So that's 200 milliamps going through the resistor.
Yep, that's about right. Yes, it is.
So the Zener diode, I don't want to say it's acting like a resistor because it's really not, but it's I don't know what the right word is. How do you describe what it's doing?
It's a regulator.
There?
It's a voltage regulator. That's all it is. It's a voltage regulator. It's acting as it's acting as a reference voltage. It's just put it that way. It's saying, okay, I have 5 volts, and whatever's in parallel with me is going to be 5 volts. If you want to look at it that.
Okay, and without that load resistor up top, RS,
yes.
The load RL would be saying 12 volts.
No, it would no. As long as the Zener diode's here, right here, it doesn't matter. This RS is protecting the Zener. That's all it's doing is protecting that Zener. That's all that RS is doing is protecting Zener. That RS is just a protection for the Zener. It's like trying to take 8,000 gallons of water and dump it into, drink it all at once. You're not going to be able to, you'll get sick. That Zener diode is like trying to take 12 volts and dump it in. It says no. Give me time to get to that point. So remember, it's that ramp up time. We don't want to do everything instantaneous. So we're doing it slowly. That's what RS does. It slows things down a little bit.
Okay, so then I have to go back to the first diagram that you drew, which had just the Zener and the load in it and the battery.
Yes, that was just me doing an example. Yes, go ahead, sir.
Yeah, so the source voltage was 10 volts, and we talked about 10 volts going out to the load.
Yeah, it would be a little less than that, just a little bit. But I'm just saying that in this practical example I did, if you have source voltage, it's 10 volts, our Zener was 10, then you would get just under 10, about 10. Yes.
Okay, so we're getting the stuff that's beyond the Zener, that's parallel to it, is getting the voltage that the Zener is rated at.
Yes.
As long as the Zener is getting that much voltage or more from the source.
That's correct. Yes. You always want to give it at least. I think the recommendation is at least 50% more voltage. 50% more voltage than your whatever your Zener is or any regulator is. That's being safe. That's giving you some safe something. Gives you a little bit of a safe boundary to play with.
Okay, thank you.
One last part I want just going to give you here is the power of the Zener, and that's something that's just really simple. The power of the Zener, and that's how much power the Zener's drawing, and that's going to be equal to, that's your V Zener times your I Zener. And the reason for that is we want to see if we're drowning the Zener. You know, if you put in you buy a half-watt Zener and this thing's pumping out 1 watt, that's a problem. That's a problem. So if we take V Zener is 5 times that by I Zener is 150. Yeah. So I get 0.75 watts of power, 750 mils. We are so close to that 1 watt on here. This is so close to that 1 watt. So let's say that this is 750 milliwatts. I designed the circuit up for 1 watt. We are so close to that threshold of that Zener. So if I was gonna, if I was gonna repair the circuit and I looked at these specs and I said, okay, what kind of Zener do I need to get? I would be going with like a 1.5 watt to 2 watt Zener. Because we're at 0.75 and that's close. That's close to 1 watt. You never know what you're going to do in the future, what's going to happen to the circuit down the line. It could increase as things get older, things increase, right? We've seen this happen. How many people are doing okay so far? Can we get a thumbs up, an okay at chat? Okay, so far so good. I'm going to get a little bit more involved in this. We're going to put this thing on to see how it works in a second here. Let's see how good our math is. Let's see how good our math is. And then what we're going to do is build one off of multi-sim. I'm going to go back to the other circuit. We're going to build one. I'm going to bring up some Zeners I have. I got some 4.3 Zeners. I thought I had some 5-volt Zeners, but I could check my box that I have. So took like tons of stuff from there, but I'll show you what I got here. See, I got some 2.4s, I got 4.3s. I even got some 16 Zeners. I don't know what they're for. I found them. And I got some 6.2s. We'll probably play with some of these 6.2s or 4.3s, but it's all good. All right, so let's run the simulator on this and see what happens. Let's run the simulator on this. So I'm going to do is erase some of this stuff and see how close our values are. So first thing I got to do is I'm just going to clean this up so I can see this. So this is going to be a 35 ohm resistor. So I got to change that value. I know, Victory, did you have multisim?
Yes, I do have it.
And I did send you did I send you this file for that? For multisim?
You sent 4 PDFs, yes.
Okay, so I sent the PDF, but I did not send this multisim file to you. Is that correct?
I don't recall, but I have to take a good look at it.
Okay, so if you ever want to set this one up, okay, just let me know. I can send this file to you, okay?
Okay, thank you.
You're welcome. So this one, double clicking on here, I'm just going to get room. Value 35 ohms we did, right? That was 35. So I just changed it, 12 volts. I'm not changing any other specs on here. I'm going to keep all our values to see what they are. I'm going to do is move things around here a little bit so we can actually see them. So IS. So here's our power through a Zener. Whoops. That's our power through a Zener. I'm moving things around here. Hate when that happens. Okay, so we have, I'm just gonna get rid of some stuff here. There we go, 5 volts output. Okay, let's run the simulator. And I'm gonna do place probe voltage, and I'm gonna do that down there. I'm gonna make this bigger, so just give me a second. Not that big, Charles. There's our voltage. So the Zener is, like I said, it's 0.08 above it, but it's still okay. You know, it's still within reason for it. Let's place probe. I'm gonna put power probe, voltage and current. I'm gonna do a power probe just right here. And that's interesting. Our Zener is a little bit higher than what we calculate. We calculate 750 mils. So I bet you that's kind of interesting. Okay, that's okay. What else do we need? We need it. Well, it says 5 volts across there. Let's see if we get the current. I'm going to go ahead and just put a new one here, current and voltage. Current and voltage. There we go. Okay, I'm going to erase some stuff here so you can see it. So okay, so we have current is, oh, you know what happened? I forgot to change this. This should be a 100 ohm resistor. I did a 100, didn't I? That's why we're getting some weird answers here. Nobody caught that. There we go. 50 mils, 748. There we go. Perfect. There's our math. Okay. So 5 volts across this. Pretty good, right? 748 through this Zener, which is what we calculated. Let's check the current out over here. Place current. And if you notice, my arrow in my current is pointing downward. This is actually using current, the current flow, not the conventional flow, which I normally do. So I'm going to shrink this guy down a little bit here. There we go. 198 mils. There we go. 198 mils. Pretty good. So right on the specs of where we did math. Is there any math that we're off on? You want to build one now? And then we'll calculate all this stuff out for us? Let's do it. Let's build one of these things. All right, let's build one, and then we're going to go on to we'll talk about the, by the way, I hit everything on, it's on page 878 and 879 of your text. Grobes. Okay. By the way, this is very short math stuff, so we're done with the hard math. It's done. We're finished. We're finished with math. By the way, if anybody wants to know what a heatsink is, these are heat sinks. I'll show you all these things out today too. So, all right, let me switch over. Let me switch over. Okay. All right, the question I had was when we did this. So the basic question was 6.2 and a 4.3. So let's see how that would be set up in our circuit. I'm going to shut the current down. So basically what I need to do is put these two in series with each other, and we'll do the math first, and then we'll see what comes up. So there's my 4.3 on the bottom. Okay, 4.3 on the bottom. And there's my second one. So that's how it's set up. Can everybody see that? Pretty good? Okay. Okay, so if we have 6.2 and 4.3, let's add those two. So we take V Zener. So if we take, we want to know V Zener total, VZ total. That's going to be V Zener, let's call it VZ1 and call it VZ2. We take VZ1 plus VZ2. So in this case, give me the total Zener voltage. Somebody give me the total Zener voltage on that.
$10.5.
Okay. You can put it in the chat too if you can, if you want. Victory 10.5, okay. 0.5 volts. 82 ohms, my resistor is still 82 ohms. So I should get 10.5. Let's see if we actually do. Okay, here we go. What happens if I turn the voltage on? Remember, my source voltage is 20 volts. 9.8, pretty close. 9.8, 9.9, 10, 10.5. We're off by 0.5. I bet you anything one of these Zeners is probably not at 100%. 3.62. There's that 3.62. Looking at, see what these Zeners are at. 6.2. So this Zener is off a little bit. Let me see if I kick this guy up a little bit. This 4.3 is not acting as a 4.3. I'm going to see if we get it up a little higher. That's a little toasty. Okay. And it's still giving me around 3.5. 9.8. So technically, we're supposed to be getting about 10.5. We get about 10 volts on it. We're off by a half volt. Not too bad on it. But let's look at what happens if I do this. This is the key point here of this whole part. So if you add Zeners, you're supposed to get the Zener voltage across it. So what if I move the, let's take this part right here, and I move it right here. So I'm going to say that A right here is going to move to this point right here. So we're going to move it to that point. So I'm going to say that point right there, yellow. So we're going to take A, so this whole wire is going to come off here. It's going to be over here. How much voltage do you think we should get across that? So if we move this point A to this yellow, let's call this to point, point 1. So we move point A to point 1. How much voltage should we get across it? You can put it in the chat if you want. So we're moving point A to 1. So this point A, so this guy is coming off. We're just going to take that off and rip it and put it right there. So how much voltage do you think we should get across that? How much voltage you should get right across that?
6.2.
Okay, 6.2. All right. So I'm going to say now our voltage at 0.1 PT1. So we got 6.2 volts. Okay, what else do we have? Victor, what do you think? You typed it in. Brett and Drake, tell me what you think.
Which one
I'm
are
a
we
little
solving for?
confused. Can you back it up? Because I don't know how we get to the point for A.
Okay, so point A is right now attached to this point right here. Let's call this point X right now. Do you agree with me right now? This point is here. So we're going to take this wire off. So I call this point A. It's right here. So I'm going to take this wire off. I'm going to put it down here. So it's basically going to look like, that. So this is going to get removed. So what I'm going to do is tie that right there. How much voltage do you think we should get across that?
I'd say 6.2.
Okay, we got 6.2. Victory, what do you think?
Yeah, I agree with that because we're using the voltage from the Zener, and that would be the voltage that we use, right?
Okay. All right.
I guess that was crazy.
Nope, you're good. So far, so good. Good explanation. Good explanation. And who else do we have? Brett, Drake. He might be around.
I said 6.2.
Oh, Drake. Okay, Brett. Then knows Brett. I decided my mistake.
6.2.
6.2. 6.2. Okay. All right. Let's actually see what we get. And let's make sure that when we do this, and I'll do an explanation if there's any difference. So I'm going to do that. Ouch. Okay. Four point three. 4.3. Let me explain to you why. So, we all agree that this is ground down here. Do you agree with me on that? This is ground down here. Isn't this a voltage divider right here? So this is basically a voltage divider. So we have this, remember back at DC, I talked to you about voltage dividers where we could use resistors and then tap off those resistors to get voltages? This is similar to that. So we can actually do is tap off. So I could have 5 Zeners in a series in a row here. Yes, they do add up. If I go from here to ground, yes, they do give me a total of 10.5. But because I'm going from here across this one only, I get 4.3 volts.
So we really need to look for the branch that's in parallel with the load.
That's correct. So my drawing is a little harder to see, and I can see that that's probably one of the reasons why you had a hard time identifying that. So let me redraw it so you can see it. How's that sound? So all I did is basically say I disconnected it up here and I put it down here. Makes it a little bit easier when you can see it visually, huh? Yeah. That's what I'm afraid of. That's VZ1, this is VZ2, that's 4.3, 6.2. So basically, we could do it that way, right? Does that make more sense? Okay.
Yes.
All right. Questions? Questions in regards to Zener Diodes? They're great. They're great. By the way, just out of curiosity, if I threw a diode up here, just a regular diode up here, that acts as a voltage source too. How much voltage do we cut off of diodes?
0.7.
0.7 you said, or 4.7?
0.7.
0.7.
0.7.
Yes, yeah, you're correct. So if you added a diode in here, that would be 4.3, 6.2 plus 0.7. Isn't that interesting? Yeah. That just
So
proves.
Charles, I have a question.
Sure, go ahead, please.
And my question is, you did across PX. So what was the voltage across A?
From this point here to ground down here?
No. From this point, from the top one all the way to the corner.
This one to that one?
From there, you had A over here. You had A right there where nothing's at. Oh, what the hell?
Right here?
Yeah.
Yeah, all I did was say, okay, I'm just broke this. So I took this part here and I just moved it down and went across it. That's all I did. So I just wanted to show you that, okay, I removed this part right here. I took this load and I moved it down across that. That's all I did on that.
Okay, so what was the voltage across that? 4.3?
Across this 4.3? Yep. V load is equal to 4.3 volts. Yep. And
okay, thank you.
And is this one right here? See that guy right there? Actually, let me do this. Let me build this thing up a little bit so you can see a little better. How's that? Could do that. This is gonna get a little toasty. Yeah, it's a little toasty. So if I take and I move these guys across, it's only take me a second to build it. Unless I run into problems like normally. Okay, there we go. There we go. So I got that. I'm coming back. Just give me a second. I'm just building a circuit. Okay, there we go. Naturally, I picked up a breadboard that's brand new. Is that pretty good? So if I take my meter, can you see the meter? Or is it still off? Okay. Let me make sure I get the source voltage here. 20 volts. So if I go from this point to that point, 4.3, 4.4. A little better with it spread out instead of being bunched up. Okay. So, Zener diodes are great. The bad side of Zener diodes is current limiting. That's about it. They're cheap, but there's current. You can only get so much power out of these things. So, if you want a Zener diode that gets 2 watts on, you're going to spend a lot of money on it. At that point, you might as well build yourself a 7805. And that's what we're going to look at right now is a 7805.
So Charles, what would be the rationale for using a Zener for a voltage divider rather than just some resistors?
Apologize. Number one is Zener diodes are regulators, and they are going to lock in the voltage. Load resistors will change depending on your circuit itself, so they can vary up and down a little bit. So load resistors are not always the best, but they're practical when you want something quick and cheap and dirt and easy. We use them quite a bit in circuits that we're taking like a reference voltage on it. But if we're trying to control something on another end, such as a microcontroller or something, and we need that 3.2 volts, and we need it exactly at 3.2, Zener is where we want to go. And they also will they will see what goes on in the circuit, and they'll keep that voltage really at that 4.3 or 6.2, whatever it is, exactly, all the time.
So the resistors, to put it another way, will consume some of the voltage, but if you have an uncertain or varying input voltage, you're going to get an uncertain or varying output voltage past the resistor, whereas with the Zener, you'll get either you get what you're supposed to get or you get nothing.
That's correct, yes. Absolutely.
Got it. Thank you.
You're welcome. All right, so we just talked about Zeners. Let's do one last one tonight, and we're going to talk about the 78, what I call the XX series. We're going to start with the 7805. I'm going to switch back to the multi-sim in a second here. So we actually call this 78XX series. When you have the 78XX, that means that these are a voltage regulator series. And what they do is they come into a package that looks like that. So the 7805 series, sorry about that. If this is facing towards, so the numbers are facing towards you, that's going to be in, ground, and then pin 3 is out. Okay? So this is going to be in, ground, and out. What's interesting is that our ground pin, the middle pin, and this base pin right up here, this metal sheet, are all tied together. Usually when you have these type of regulators, you need a heat sink with them. A heat sink looks like this.
Hey, Charles, were you going from left to right or right to left?
I'll repeat it in a second here for you. Just give me a second here. All right. So this is my left side. So that's my left. So that's in, ground, out. So it's pin 1, 2, 3. And this part right here is ground. So this is pin 1, 2, 3. 3 is out. 2 is ground. And pin 1 is in. Now, like I said, these things give off a lot of heat. But what's nice about these is that they're a little more expensive, just a little bit. They're not too bad. But if you want this to be locked in at 7805 compared to the Zener, this will never change at all. This thing will stay right at 7805. These are called voltage regulators. You see these quite a bit in power supplies. They have different numbers from different manufacturers, but they're all similar to the same characteristic. They also have thermal protection in them. So if you start heating these things up, they will actually shut themselves off. The other thing nice about them is that the heat sink on this is all tied to the metal part is all tied to the heatsink, which, let me see if I can pull up another heatsink. I'm trying to find one that actually looks better for you. This is one that is a 7805. Let me move this one out of the way. But here's one that is with a heatsink. You notice that we have a nylon backing. It's basically a thermal backing to it. That's that blue. And then we have a screw to it. So this part right here, these fins actually take that heat off of it. This thing does not like heat. So a lot of times on your regulators, you'll have a heat sink. You may have a fan too with them, involved with them. So let me go back to any questions in regards to them. Okay. All right. So I'm going to go ahead and just going to keep these guys on the side. Actually, yeah, I'll keep this guy. Whoa. Oops. And I'm just going to I'll just bring up new ones here. That's all I'm going to do. I'll just keep that one there. All right, so the 7805. Why is this thing bouncing? Looks like that. So if we have I'm going to change this to a 100 ohm resistor. So if you see that, so this would be 1, 2, and 3. So VRL, if this is a 78, this is how you read it. If you see that, if it's a 7800 series, the 05 tells you the voltage. So if this was 7812, this would be a 12 volt regulator. If it was 09, this would be a 9 volt regulator. So if we have 12 volts in, and this is a 5, how much are we going to get out of here?
5.
5 volts. And boy, this is going to look like this. Remember on your test, I had this on there too. So let me draw this out a little better. There we go. So if this is 5 volts, this is not going to move at all. How do you get rid of all these little ripples up here? Capacitors, right? A big capacitor right here. And we also sometimes put a capacitor on this end of it. And what that does is give it a little more stability. So this could be about a 1000 microfarad. And this one would be like 4700. So that's just like what you have. So we could have our bridge rectifier come right into this thing, and then we can have this 4700. So this could be our bridge right here, right? This could be our bridge. Then we bring this into the 4700. We may get a little bit of ripples, fine. Hopefully you don't get any. If you do, put another capacitor in parallel. That's not too hard on that. And then the output right here is connected to the ground, so they're common right here. And this should give us 5 volts. So IRL. So why don't you come up and tell me, and not come up, but why don't you tell me what the current is on this? So using Ohm's law, if we have resistor, and this R2 is RL. So if this is RL down here, how much is up here?
$5 volts.
Yes. And RL is 100. Okay. So that gets us about 50 mils.
Yep, 50 is correct.
Well, I'm glad my brain is at least working tonight on that. The last couple of nights I've been having to use a calculator on some of the simple math. So, all right, let's build this circuit. Any questions so far about the 7805? Let's go ahead and build this thing. Next week we'll do a 12, and well, maybe we'll do a 12 tonight, but next week definitely LM317, and then we're just gonna take our time on that. The LM37 gonna take us a little time to do, but these are not. These are fun. These are fun. So let me go ahead and switch back over. Okay, there's our board. I'm going to go ahead and I'm going to still get to use a 82 ohm resistor since we're still using the 82s. So on the circuit, there's my resistor. That's my load. Okay. 7805. Actually, I'm just going to go ahead and tie it to the third pin right there, just like that. I'm just going to bring them down a little bit so you can see it. Bring this up. Is that better so you can see all my wires? Okay. So our VN, and our VN is going to be 20 volts. We're just going to keep it at 20. So all I'm going to do is I'm going to bring the VN. And I got my power supply shut down for now. My ground, I'm just going to ground it down here. But now notice that I need to take this middle one and bring it down too. So if we have 20 volts in, and this is a 5-volt regulator, what should we get out? What should we get out on it?
5 volts.
5 volts. Okay, let's see if we do. Here's something interesting on it too, on these regulators. On the Zener, you draw a lot of current on your circuit. A lot of current, a lot of power. On our voltage on this power supply, on this regulator, 7805, I'm going to show you something. I'm just going to move my setup here. I'm going to show you something here. We're only drawing about 60 mils. We're only drawing 60 mils on that. See that? 0.06 right there. That's pretty. That's another reason why the regulators are awesome. These what they call chip type regulators is that they don't draw too much. Why? Why do you think they don't draw too much? Can somebody try to give me a reason for that? Brett, what do you think the reason is for that? Drake?
I'm actually not quite sure.
Okay, that's fair because I'll tell you, it's you. Did you ever take the? You didn't take the 206 yet, did you?
No, I have not.
Okay, that's what I figured. If you haven't ever taken the 206, in the 206 class, which is our transistors class, all chips are made up of transistors. So, number one,
Silicone, right?
what's that?
You said transistors made out of silicone, right?
That's correct. Most of them are made of silicone, yes. So a transistor is a circuit that doesn't technically have to draw a lot of current, right? So it doesn't take much to draw. The nice thing about a transistor is fast switching. It's fast response times. There's another reason for them. So that's the reason why they're not. We use transistors on here, and they're not power hogs. So I put my DC back on. Hopefully, whoops, you can't see that. There's my circuit. There we go. Okay, I'm going to measure across it. By the way, this thing is getting a little toasty here, but we'll do some measurements and then do some calculations on it. Ready? So across it. 5 volts, right on the money. That is the reason why these things are widely used in industry. When you need something for precision, it's going to give you precision. I'm going to kick the voltage up to 25 volts. I got to be careful because there is a voltage max on these chips, and if I see that, I could actually shut down the chip. So I'm going to kick it up to 25 and see what happens. Nothing. It's still staying put. Okay, so I'm going to bring it back to 20. I'm curious to see what's going to happen when I add some load to it. What do you think is going to happen when you add load to it? Do you think it's going to stay at 5 volts? What do you think?
Actually, Charles, before you get there,
Yes.
if you were to continue ramping the voltage down, at what point would it cut out or fail to deliver 5 volts?
Let's figure that out. Let's do that right now. Let's see what happens. Let me grab some leads. So I don't have to hold on to it. I'm just grabbing some leads. That's an excellent question. So I got some leads. So I'm going to do is take my probes and I'm going to go ahead and just connect them up. And I'm going to put it across the regulator. I'm going to put it across this regulator right here. Let's see what happens. So let's bring this up a little bit and see, do I have it negative or backwards? Yeah, I do have it backwards. I don't want to confuse you guys. Okay, here we go. 4.99, 5 volts. Remember, I got some extra leads in here now, so it's gonna be a little bit. It's about 5 volts, but that's because they have some extra leads that are going on in here. There it is. All right, let's do this. Let's bring it down. I'm gonna bring it down 2 volts. I'm gonna bring it down to, still holding at 5. That's 18 volts. 16. 13. 11. Let me ask you something. What do you think when do you think it's gonna start cutting off? Before I go any further, right now I'm about 10 volts. What do you think is gonna start going off?
Well, I would expect it to absolutely cut off at 5, but does it start to fade before that?
Well, we're not fading yet, are we? We're still holding. There's 6. 6 volts. 6.6. There's 6.2. 6.1. About 6 volts. Keep going down. Basically, it'll just start. All you got is 4 volts, so you're not going to get any more on this thing. I mean,
so does the Zener have a voltage penalty like the other diodes do?
let's investigate that real quick too. Let's investigate that. It's not a bad idea to investigate that thing. I'm going to use the 6.3 volt regulator Zener with my 82 ohms. So I'm going to do is I'll just change out the leads on this. Similar setup. Okay. And there is a lab that I usually have you do with the Zeners. I did get something when I did not do right. Oh. Okay, 6.4. So 6.5 right now, we're Zenered, okay? That's across the Zener load. Okay, let's see what happens when we bring it down. So I'm going to bring it down to 15. You see it's a lot more, it's fluctuating a little bit more on the, toward the, if I go back up, you'll see that, let's go 20. Watch it, 0.56, 7, 0.8. It's a little more sensitive, isn't it? So right now that's 17, 16, 14. There it is, we're down to 6.3. And we're only at 12 volts. 6.0. 5.5. So if we lost it out, this is 11. So you can see a Zener diode is not as, it does not lock it in as much as the voltage regulator, right? So right now we're at 5.6. So let's see, find out when it really cuts off, totally cuts off. So right now at 9.4, I suspect around 6. 3.5, 7 volts at 3.5. So 8.3 gives me 4. So you see it's a lot more sensitive. It doesn't have that feedback circuitry in it. So you can see that. Does that help you?
Yes, it did. Thank you.
You're welcome. So which one would you want to use in industry? Which one would you want to use in industry?
The 7805.
7805, yeah. If you really need precision, 7805, absolutely. Yep. What are Zeners used for? Quite often we use them as reference voltages. They're great for reference voltages. A lot of times we need a reference voltage on a controller, and we don't need that. There's no load to it. It's just the reference voltage, and we want to make sure that reference voltage stays exactly at it. So, for example, we want a 6.2 voltage reference. And this is checking to see if our power supply is working correctly. So what we'll do is we'll measure the voltage across it for that reference voltage, and we'll bring it to a comparator. That comparator will go to a processor and say, hey, if I drop below this, we got a problem. We'll shut down the circuit. So a lot of times our Zeners are not used really for loads. So just give you an idea on that one. They can be for cheap things, but when it comes to precision and some high current things, no. All right, I'm putting 282 ohm resistors, and that means we have approximately 41 ohms of total resistance on here. So our current should go up if I get this guy in. Well, maybe I can't get him in. All right, I'm just gonna put this guy in parallel. So now I pretty much, our current should go significantly higher on this circuit. I'm gonna go back to our original. Get that guy out of there. Our voltage just doubled on the power supply, which basically says, hey, we just had double on the we had a double load resistor. See, double load resistor. But guess what? We're still locked in at still locked in at 5 volts. We're drawing a lot more current, and this regulator is getting a little warmer, but it's not too bad right now. But it hasn't changed. We're still at 5 volts. We're still at 5 volts. Actually, let me put it back up to 20. Sorry, it was at below that. There we go. Still at 5 volts. Hasn't changed. That's because of the feedback circuitry that's inside that chip. These are called chip regulators. These are called chip regulators. Any questions on this? On the 7805? Give me a thumbs up if you